Okay, shall we start now? Can you see the screen?
Yes.
Okay, so I selected a couple of questions from mid-semester exam and the final exam for this previous batch, covering some concept related to DSP and the chapters we basically covered. So the first one is this. So this is the part of the first question appeared in the mid-semester exam. So you should have to have a kind of idea how do we plot the discrete signal and how we can manage to get different versions of the discrete signal like mirror image, shifted versions, scaled versions like this. So this is one example for that. So sometimes you will be given a kind of a discrete signal in the form of numbers like as we discussed initially. So xn would be like this. So within this curl bracket you can have like 2, 1, 4 like this, and saying that this is the origin of the discrete signal. So this is the x0 value actually. So without having this arrow, you cannot basically find a place where I will have. So you cannot plot it because you don't know the reference of the signal. So that's why we put this arrow to indicate the x0 value. So this is one way of representing a discrete signal. So the other way is like we can use some mathematical way of introducing this discrete signal. So this is a kind of example for that. So now this xn is defined using a kind of a mathematical form. So if you basically yeah, so in the first section, so they asked to determine its values and sketch the signal xn. So if it is the case, so this signal is basically defined from minus infinity to plus infinity. And it's a kind of a piecewise discrete time. So the functional values are basically like this 1 plus n over 3. So this is basically valid only for the values in between minus 3 and minus 1. So then if you want to find the x minus 3, so this is the functional value. So you can just substitute minus 3 into this n. So then it becomes like 0. So then if you want to find x minus 2, just plug it to here. So then because this n equals minus 2 is basically within that range. So this is the corresponding functional value. So you can just substitute minus 2 to n. So then it becomes like 1/3. So likewise, you can find values up to n equals minus 1. So then the next partition is like, so the functional value is 1 from 0 to 3. So then if you want to find x0, so which is basically included into this range, so the value is 1. x1 to x3 is basically having a value of 1. So then, so the third partition, 0 otherwise. So it means like, So whatever the values outside these definitions, outside this range is basically 0. So for example, it means like x minus 4. So this is 0. X plus 4. This is again 0. So likewise, you can simply find these discrete values, discrete samples by considering the ranges given. So if you want to evaluate the value in between minus 3 and minus 1, so you have to select this. So you have to select this as a function. If you want to find the values in between 0 and 3, so this is the value. So if you want to evaluate the value of n outside these two regions, so then you have to stick it to this. So then you can simply draw this discrete signal. So this is a discrete signal. So your x-axis is n and your y-axis is actually xn. So this is 0, 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, minus 4. So you can just plot it. X0 is actually 1. X1, 1, X2, 1, X3, 1. X4 is 0, X5 is 0, X minus 1 is actually 2/3, then 1/3, 0, 0. So the value here is like 1, value here is 2 over 3, value here is 1 over 3. Okay, so this is the way we can simply illustrate a discrete signal if it is defined as a mathematical function. Yes, so then the second is like sketch the signals that result if we first of all take the mirror image xn and the delay the resulting signal by 4 samples. So how do we do it? Okay, so now we basically obtain this xn. So you can easily get the mirror image of this xn. So the mirror image is actually, if you take the mirror over this y-axis, you can simply get the mirror image. So you have to take the mirror over this y-axis. So folded signal means is actually mirror over the y-axis. So it means you can simply rotate it by 180 degrees. So then the signal would be like so the sample at x0 is remains as it is, and this sample moves to here. So now it's something like that. So this is moves to here, this moves to here, and this 2/3 is simply moving to here. Sorry, yes, 2/3 is moving to here, 1/3 is moving to here, then 0, 0, and so on. So hope it's clear. So you can simply take the rotation or a mirror or y-axis. So assuming that this y-axis is acting as a mirror, and you can just plot the samples according to that. So then you can see the mirror image of this xn or the folded version of this xn. So we define it like x minus n. So this is the folded version of this xn. Okay, so then it's asked you to delay this signal. So keep in mind, if it is a delay in signal, so it's like this. So so you have to push it to the right hand side. So you have to move the signal to the right hand side. So it means like if your signal is xn, so the delayed version is like xn minus n naught. Okay, so if your signal is xn, your delayed version is xn minus n naught. If your signal is x minus n, so the delayed version is actually x minus n plus n naught, having the same delay for this forwarded signal. So it's like this. So you can interpret this as x minus n minus n naught. Because this is a mirrored signal, your variable is actually considered as a minus of this random variable. So this is your random variable, so it's with minus sign. So you can take this minus sign out and have this kind of a modification. So that's why it's like minus n plus n naught. Both signals are simply shifted to the right hand side. If it is a time advancement, time advance, so this is a time delay. So this is a time delay. So this is time advance. So this is simply xn is the original function. So it's shifted to the left hand side. Then the time advance of xn is n plus n naught. Okay. So then what we can simply do is, so this is the original xn. So you can move this xn to the right hand side by 4 samples. So it means like, so this 0 point actually moves to n equals 4. So then you can do it easily because now we have this forwarded signal. So we can push it to the right hand side by 4 samples. So then the sample appear at 0 point is simply moved to n equals 4. So then the samples appear at -1 is moved to n equals 3. So likewise, you can simply shift this discrete sequence by 4 units to the right hand side, which is the delayed version of the signal. If you want to have a kind of a time advance signal, so you have to simply shift this entire sequence to the left hand side by the amount that's specified here. So I believe like we can do this one. So this is like simply push this entire sequence to right hand side by 4 units. So then the second is actually first delay xn. So first delay xn means now we have this xn which is basically indicated in red lines. So delay xn by same amount, it means like you can simply shift this discrete sequence indicated in this red stems by 4 units to the right hand side. Then you have a kind of a version like x in minus 4. So then take the whatever the signal you basically obtain here can be simply rotate over y-axis by 180 degrees gives the mirror of this one. So then you can compare whether these two signals are same or not. Okay, so hope it's clear. So this is the simple example how we can basically represent a discrete signal. So if you want to basically if you want to represent this signal using the delta functions and unit step. So we have this unit impulse function, which is defined as delta n. So this is delta n is the unit impulse. So if you draw it, it's something like that, n. So this is at n equals 0, the magnitude is 1, so this is delta n. So then we have this unit step. So this unit step sequence, so this is something like that. So this is unit step. So if I ask you to simply represent this as a unit step, or the combination of this unit impulse and unit step, so by looking at the behavior of this function, you can simply say that we can basically demonstrate or represent these set of samples from n equals 0 to upward. So the values from 0 to plus infinity, like un minus un minus 4. So then this basically we covered these samples, these 4 samples, un minus un minus 4. So un is the original signal and un minus 4 is the shifted version of this un. So if you just subtract these two together, so you can simply remain these 4 samples. So then you can represent these set of samples at n equals minus 1 as 2/3 delta n plus 1, and this is like 1/3 delta n minus, sorry, n plus 2. So then xn can be simply represented as like 1/3 delta n plus 2, 2/3 delta n plus 1 plus un minus un minus 4. So this is basically covers the samples between 0 and plus infinity. So these two basically covers the samples at -1 and -2. Rest are 0, so you don't need to worry. So this is the way we can simply represent this whatever the discrete form as a function of delta and uns, unit impulse and unit step functions. Yes. So then the second is actually so this is the questions I referred for the next. So show that the fundamental period NP of the signals skn equals e to the power j 2 pi k n divided by capital N, k goes from 0, 1, 2 and so on, is given by NP is the fundamental period is equal to n divided by GCD of k and n, where GCD is the greatest common divisor of k and n. So how do you approach to this question? So, so these here you have series of signals. So it's not just a one signal; it's a series of signals. 2, 5, k, n over n. K goes from 0, 1, 2, and so on. So once you substitute k equals 0, you have a one signal. If you substitute k equals 1, you have another signal. So likewise, you have like S0n, S1n up to whatever the maximum value defined for k. So you have set of signals. So it's not just a single signal. So by looking at this, so the exponent of this function, so we know that if it is a complex function, so it should be in the form of e to the power j omega. E to the power j omega. So if it is like a, so you have this skn, so it's like skn is actually like this. So this, so you can have, yes, this is, so then what we can simply do here is map it with this standard complex exponential function. So then you can claim that omega would be like 2 pi k over capital N. Because this N is the index of this signal here. K is basically giving this series of signal. So the in general, omega, or the angular frequency of this signal, is series of signals, is basically 2 pi k over n. So once you set the value of k, so you can basically have the angular frequency of each and every signal. So this is the angular frequency of the signal. So we can basically extract it from this one. So it's like j omega n skn. So this is the angular frequency. So once you derive the frequency of the signal, so it's like k over n. Because we know that omega is actually 2 pi f. So based on this statement, you can simply get the frequency of the signal as a ratio of k and capital N. So what is the GCD of k and n? GCD of k and n. So let's assume we have a GCD value, greatest common divisor, for these both numbers k and n as alpha. So alpha is the GCD of k and n, capital N. So if this alpha is the GCD, so we can represent k as a function of alpha into some kind of a value. Okay. So similarly, capital N also can be represented as a function of alpha, which is like this. Okay. If this is a discrete signal, if it is a discrete signal, we know that N is ideally the period of the signal. N is ideally the period of the signal. If you remember the definition of these ones, so this capital N is actually ideally period of the signal. So then from this we can simply say that N dash can be represented as N over alpha is GCD of K and N. Normally, if it is a fundamental period for the series of signals, we should be able to represent this as this. So N dash actually would be the fundamental period. If this is the fundamental period, you can simply represent the periods of these other signals as a multiplication of this NP. So it may be like NP times 1, NP times 2, NP times 5, NP times 7. Likewise, you can represent the period of this set of signals as a function of NP. Now with the common GCD, we represent the general period of this function. So this is the period of the function in general. So period of the SKNs in general. If we have a fundamental period, it means like there should be a value for the fundamental period which and the periods of these set of signals Skn can be represented as a function of NP. So it's like this is the period of this function signals Sk. It should be represented as a kind of a K times NP. So NP is the fundamental period. So N is the period of the signal, period of SKMs. So from this GCD, now we found that the period of this signal Skn can be represented as a kind of a constant times the fundamental period. So then simply we can obtain the fundamental period of the signal in dash for this case, so NP is actually capital N divided by GCD of K and N. So then we can claim that the fundamental period of this set of signals can be represented as N divided by GCD of K and N. So then, okay, so you have to find the fundamental period for this. Okay, so let's have like K values 0, 1, 2, 3, 4, 5, 6, 7, and so on. Capital N is actually 7. For all these cases, capital N is actually 7. Okay. So then what about GCD? GCD KN. In this case, it's 7. So the GCD of K and N is 7. For this case, GCD of this 1 and 7, 1. Here it's 7. So then N divided by, or the fundamental period is actually N divided by GCD. So this is 1. This is 7. 7. This one. So this is the fundamental period distribution for this different set of signals. Next we move to yes. Yes. So this example basically refer the Fourier transform. So we can derive the Fourier transform, then make it discretize, then it becomes a discrete Fourier transform. Then again, we use this fast Fourier transform techniques. So using this computationally efficient mechanisms, we can derive the discrete Fourier transform. So then it becomes a fast Fourier transform. We discussed two methods to evaluate fast Fourier transform. So using decimation in time and decimation in frequency. So this is simply the Fourier transform of a signal. Here this xn is defined like this. Xn is actually a to the power n un, and a, the magnitude of this a is less than 1. So why we define this condition is like to make it absolutely summable, so you have to maintain this value. So we'll see like where we can apply this condition. So your xn is actually now this. Xn equals a to the power n un. By looking at this function, you can simply say that this is valid for n greater than or equal to 0, because you have this un, unit step function, which is defined from 0 onwards. So then this xn is actually right hand sided function. Right hand sided sequence. Okay. It means like if this is your n, so the sequence is simply appear here from n equals 0 to infinity. If it is a left-handed function, so your function is basically happy in the negative values of n. If it is a both side or dual side sequence, so then the function is defined from minus infinity to plus infinity, so both positive values of n and negative values of n. Yes. Now, so it's asked to evaluate the Fourier transform of this. So we'll take this Fourier transform first. Yes, x omega. So this is a discrete sequence, so you can apply the Fourier transform for this one. So if it is, if I remember the definition of this Fourier transform correctly, so it's like minus infinity to plus infinity xn e to the power j omega n minus 2 plus. Okay, so if you simply apply this definition for this function, so we know that this function is defined only for positive values of n. So then you can truncate this summation and simplify it like n equals 0 2 plus infinity. Xn is now an. Xn is now an. E to the power j omega n. So then we can further simplify it. It's like 0 to plus infinity a e to the power j omega to the power n. So now this is an infinite sum of a geometric series. So this is infinite sum of a geometric series. We know that if it is a converging sum, so this should be okay. So I actually couldn't remember this whether it's plus or minus. So better to check the definition. If it is minus, so then it should be minus here. So I couldn't remember actually the definition is e to the power minus j omega n or plus j omega n. So depending on that, so you can, I'll put some mark here. So please check that. If it is minus j, so you have this minus j here. Otherwise, it's like plus j. So let's check.
So it's minus j omega n.
Yes, it's minus. Sorry. It's minus. So then we have minus here, minus here, minus here. So then we can simply use this infinite sum of a geometric series. So it's like 1 over 1 minus this common term. So then now it becomes 1 over 1 minus. So this is the common term, a e to the power minus j. So this is the Fourier transform of this xn. 1 over 1 minus a e to the power minus j omega. So if you want to make it completely discrete, so you can simply substitute. So this omega is actually, if you remember that we obtain this continuous function discrete Fourier, we first obtain the continuous Fourier transform and make it discretized by simply splitting the omega domain into n equal spaces. So then it's like 2 phi k over n. So you can, if you want to make it completely discrete, so you can just substitute this omega equals 2 phi k or capital N and replace it, or else you can keep it as it is. So this is the Fourier transform of this xn. Okay. Now we need to find the magnitude and phase. So how do you obtain this one? So it's again very clear.
Excuse me, sir.
So you have x omega as 1 over 1 minus a e to the power minus j omega. So to obtain the magnitude, so this is like, so this is a kind of a complex number. So this is the complex number. So if you have a question, so you just interrupt me and answer.
Excuse me, sir.
This is the denominator is a kind of a complex number. So you can simply convert it to a kind of a
Excuse me, sir.
magnitude and a phasor format. So, or you can, so this is this complex number now in Cartesian form. So you need to convert it to polar. So once you convert this denominator to polar form, you can immediately find out the magnitude and phasor. So we have this complex number Z is 1 minus a e to the power minus j omega. So how do you convert it into a polar? So first we can represent it as a proper Cartesian form. So we can apply minus a. So e to the power j omega can be converted into a kind of a Cartesian form by applying Euler transform. So then it's become cos omega minus j sine omega. So then if you simply combine this real and imaginary component, we have 1 minus a cos omega. So this is the real part of this Z, and then plus j a sine omega. So this is the imaginary part of this signal or component. This is imaginary part and this is the real part. So how do you get this magnitude? It's like you can take the squares of this real and imaginary part. So it's like 1 minus a cos omega squared plus a sine omega squared. So then it's like 1 as the question answers omega. Then do we need to? Not necessary actually. You can derive the x omega. And if you want to make it like very perfect, you can just state xk by just substituting omega with 2 phi k over n. So it's not necessary if you basically obtain the Fourier transform. So of a discrete signal, we know that this transform represents the continuous version of this DFT. So the profile of this DFT, because we obtain this Fourier transform and make it discrete by simply picking the finite set of values in between minus phi and plus phi. So we know that once you derive this capital X omega, so it's the Fourier transform or the profile of the Fourier transform. Doesn't need to convert it to xk by substituting, but if you want to make it precise, you can do it. Doesn't matter. So then this is like 2a cos omega plus a squared cos omega, and here also we have a squared sine omega, altogether it's a squared. So then the magnitude of x omega is actually 1 divided by 1 minus 2a cos omega plus a squared, and the angle of x omega is actually like we can simply get the phasor of this Z, phasor of Z as tan inverse a sine omega divided by 1 minus a cos omega. So so then you can simply bring this phasor to the numerator, so it becomes then minus tan inverse a sine omega divided by 1 minus a cos omega. So then this is the so in the magnitude we should take yeah, here we have mod dz is like root of this. Yes. So this is the magnitude spectrum. This is the phase spectrum. So if you are asked to draw it, so just find the shape of this function, because we have a cos function. So this is a kind of a cos fixed term, 1 plus a squared. So the numerator is actually behaving according to the root of cos. So you can, if you want, you can simply plot it in MATLAB and see the shape of this one. And the face also, I cannot say the exact shape of the face. So you can simply plot this minus tan inverse of this ratio. So if you want to make it discrete, so you can simply uh, convert this omega to this form 2 phi k over n, and you can specify a value of n and then substitute multiples of k's. K goes from 0 to n minus 1, and then you can plot a discrete version. How that negative signs come? Yes. So the negative sign is actually, now we can represent this as 1 over, so I'll replace this denominator as a z. So then this z can be represented as the polar version mod z and angle of z. Okay. So then how do you manage this kind of a scenario? We can simply say that the magnitude of this total quantity is actually 1 over mod z, and the angle, you can bring this angle to the numerator, making it like minus of this angle. Or else, like if you represent this as a complex exponential function, so it's something like that. So x omega equal 1 over, so this here you have mod z e to the power j an angle of z. So this is the polar version of this z. Okay, so then we can simplify it like this, and we can bring this e to the power term to the numerator by adding this minus sign. So this is so then what's the magnitude? Actually this is the magnitude and this is the phasor. So the phasor of this is like, phasor is actually minus of angle of z. Angle of z is tan inverse. So that's why this minus comes to. So hope it's clear. Yes. Yes, we done it. So then we move to the next part. Okay. So the next question is this. Okay. So we have a discrete Fourier transform x, a k, if the sequence, discrete sequence is xn. So the information we have is like we have xn, which is our finite to infinite sequence. So yes, according to this is a kind of a finite sequence. So this is a finite length sequence. So the sequence length is actually capital N, and the discrete Fourier transform is simply represented by xk. Now we are asked to evaluate or represent the Fourier transform of this xen and xsn, those two quantities, where it's defined like this as a functions of xk in terms of xk. So how do you get it done? So if you ask to evaluate this xk as of this xen and xsn as a function of xk, so what we can simply do is first represent this as a convenient form to convert to this xk. Yeah, what's the definition of yeah, sorry, actually um, yes, now we can, so we can rewrite this xen like this. So we have xn here, and let's have this cos 2 pi k n away. We can simply represent this e cos term like this. We can replace this cos term as a function of e to the power j, so the complex exponentials. So then it becomes here e to the power j 2 pi k n over capital N plus e to the power minus j 2 pi k n over capital N over 2. So then if you expand this, it's something like that, half xn e to the power j 2 pi k n over n plus half xn e to the power minus j 2 pi k n over capital N. So this is actually xen. So if you apply Fourier transform, so it means like Fourier transform of xen should equals to half. This is a constant, we can treat it as a constant. Then Fourier transform of xn e to the power j, so I'll put alpha, not alpha, we'll put like this, j 2 pi k n over n, then again half Fourier transform of xn e to the power minus j 2 pi k n over capital N. So then you can apply the Fourier transform properties. So we know that if you have this xn e to the power minus j 2 pi k naught n over capital N. So you can immediately convert it to the Fourier form of x k minus k naught. So the if you add a kind of exponential term, so it's appear as a kind of a frequency shift in the Fourier domain. So if you have this k naught term here, so it's appear as a frequency shift, or this k representing a frequency actually. So the frequency shift in this Fourier domain. So then you can simply map this property or apply this property to here and here. So then you can simply replace this block with x, because the Fourier transform of xn is actually xk. So xk minus, yeah, we'll put another index here, otherwise it's like making confuse. Like we'll put k bar, k, and here it's like x k bar plus k. So the Fourier transform of this xk bar is a function of this. The shifted versions of this original xk to the left hand side and right hand side and take the scaling factor half there. So this basically refers the properties of the Fourier transform. So you should be able to apply some properties. So there are plenty of properties, but assuming that because this is an open book exam, so you can access to this all DFT properties. So you should be able to apply like very common set of properties to obtain the discrete Fourier transform of signals. Either you can use this very fundamental integrations or the summations, basic formulas or the definitions of the DFT, or else like if you can convert or format the function, like in this case, you can simply use the properties of this DFT to get the ultimate result. So there are two approaches. One is like you can stick it to the basic definition of this DFT or FT, Fourier transform, and apply this basic apply the formula for this basic definition to obtain the Fourier transform of a particular signal. Or else like you can simply use the discrete Fourier transform properties to obtain the ultimate result. So both of options are there, but sometimes using DFT properties, you can easily obtain the final answer, rather move into the basic definition and do this infinite or finite summation. So keep in mind, so most of the cases, so the applying Fourier properties would be a kind of an easy pathway to get the final answer. Yes, then yes. Okay. So let's take this example. Okay. So we have a rectangular pulse xn. So if you plot it like it's something like that. So we have n xn. So So this is the rectangular pulse in discrete domain. So you have a rectangular pulse in discrete domain. So you are asked to evaluate the Fourier transform, discrete Fourier transform, and ask you to simplify to this format. Okay. So once you apply this definition for this case, so it's minus infinity to plus infinity xn e to the power minus j omega n. So this infinite sum can be simply truncated into a finite sum because this pulse or the rectangular pulse has samples from minus n1 to plus n1. So then the summation would be like n equals minus n1 to plus n1 xn e to the power minus j omega n. Okay, so xn is actually, for this case, xn is actually 1. We can just substitute 1 here. So then we have this kind of a summation, minus n1 to plus n1 e to the power minus j omega n. So if you have a kind of a double-sided sequence to obtain the Fourier transform, so it's easy because we know that if it is a single-sided sequence having a finite length, we can easily get the summation of this n terms. So you can simply refer the geometric series. If the terms are infinite, you can simply say that 1 divided by 1 minus r. If it is a kind of a finite sequence, so you can simply say that 1 minus r to the power n, n is the number of terms, divide by 1 minus r. So you just refer the geometric series. So in geometric series, you can either find the infinite sum or a finite sum. So finite sum would be like if you have n terms, it's like 1 minus r. R is the common value. I couldn't remember the exact mathematical name for that one. In Sinhala, we use that Podu Anupati or something. So that are 1 minus r to the power n. N is the number of terms, divided by 1 minus r. So then if you make this double-sided sequence to a single-sided sequence, it's easy to manipulate. So how do you make it like a single-sided sequence? We will bring a new variable m. So m is actually n plus n1. So then the sum would be m equals. So when simple n is actually minus n1, so m goes from 0. So we need to make it a single-sided sequence starting from 0. So that's why we bring a new variable called m, which is actually equals to n plus capital N1. So then once this simple n is capital N minus n1, so the value of this new index m is simply 0. If it is n1, so this becomes 2n1. Okay. So then what happens to this j omega? Now we can replace the simple n with m minus capital N1. Okay, so then we can, so now we make it to a kind of a single-sided sequence. So we have m equals 0 to 2 and 1. And if you expand this exponential term, so we have minus j omega m and plus j omega n1. So this j omega n1 is independent of this index m. So you can basically bring this outside of the sum, e to the power j omega n1, because it's independent of this index m. So then we have e to the power minus j omega to the power m. So then you can simply replace this finite sum of this geometric series like 1 minus e to the power minus j omega. What is the number of terms? So here we have 2 and 1 plus 1 terms, because this starts from 0. So we have 2 and 1 plus 1 terms. So 2 and 1 plus 1 terms. Divide by 1 minus e to the power minus j. So then your final answer would be e to the power j omega n1 into this. Okay. So let's see how we can move forward. Now we have, so how it took the range. Yes, like, so this is the, so how many samples are there in the sequence? So if this is in between capital N1 and N1, so this is simply represent as like this. Mod n less than or equals N1 means these samples are simply packed to the values of minus N1 to plus N1. How many samples are there? We have 0. Yes. So we have 0, 1, 2 up to N1. How many samples are there? So we have N1 plus 1 sample, because we are considering this sample at 0 as well. It's just like time delay. No, this is not a time delay. So we have a sequence. We have a finite sequence like this. So we have 1, 2 up to capital N1. Similarly, we have -1, -2 up to minus N1. So we have N1 samples between this range. -1 to -N1, we have N1 number of samples. Similarly, +1 to +N1, we have N1 number of samples. And including 0, we have 2 and 1 plus 1 samples. So hope it's clear. Okay, so the last step of this one, so we have this index summation. M goes from 0 to 2 and 1. Here we have e to the power minus j omega to the power m. So this is actually a geometric series and you need to find the sum of how many terms. So this index starts from 0 and goes until 2n plus 1. If you apply the same concept here, so from 1 to 2n plus 1, we have 2n1 samples. So the index starting from 1 to 2n1, we have 2n1 samples. When we count the 0 index as well, we have 2n1 plus 1 samples. So this is a geometric series and you need to find the sum of 2n1 plus 1 samples, because we consider the 0th index as well. So if it is simply start from m equals 1 to 2 and 1, we have 2 and 1 samples. If it start from index m equals 0 to 2 and 1, so you have already 2 and 1 plus 1 samples, because we simply consider the 0th sample as well. So hope it's clear. If it is not, you just put a text. So now, so this is a geometric series. Now the issue is like, this is not a finite sum. So this is a finite sum. You need to find the finite sum or the sum of this 2n1 plus samples. Yes, why we put m is actually initially. So initially actually you have a double-sided sequence. Minus n1 to plus n1. So if it is a double-sided sequence, so you have to cater it or you have to treat it as two sequences. So you have to split this to like this. n1 to minus 1 plus 0 to n1. So I have to split this sequence into two blocks. One is referring the right hand side, the other one is referring the left hand side. So this is actually referring the left hand side sequence. So this is the right hand side sequence. So without splitting it to this level, you cannot apply these concepts of or the fundamentals of this geometric series. Okay, so that's why. So then it becomes a kind of a complicated path. So what we can simply do is, rather having this double-sided sequence with this minus indexes and plus indices, you can simply convert this summation into a right-hand side sequence by introducing a new variable. So initially this n variable goes from minus n1 to plus n1. So we'll introduce a new variable called m. So this is the new index in our case, because we want to make this double-sided sequence to a single-sided sequence. So that's the purpose of introducing m. So we need to convert this double-sided sequence, because double-sided means, see, like this is having, so this is the negative values. So these are positive values. So it's like a sequence having these values from negative side of the n and the positive side of the. So these are the negative side of the function. These are the positive values of n. So this is a double side sequence or dual side sequence. So if you want to apply this geometric fundamentals of this geometric series, it's easy to make it a kind of a single-sided sequence. So that's why we introduce this m. So how do you make it define this m? So what we want is like, we want to make this lower limit to 0. So we want to make this lower limit to 0. So how do you make it? Like if you bring this n1 here, so then it's like n minus n1 is 0. So then if you want to make it the lower limit to 0, so you can have this substitution here, n minus n1, so sorry, plus. So this is the substitution. So then if this n is actually capital minus capital N1, now your m is actually 0. So the lower limit of this new index m is 0. So the upper limit of the new index is actually 2n1. So that's why we have 0 here and 2n1 here. So I hope it's clear. Now what we can do is we can now make it a kind of a single-sided sequence. So we can apply this geometric, the fundamentals of this geometric series. So then it's like this. Sorry, this is not m. So this is m minus, yes sir. So this is m. So now we apply this geometric series. So then it becomes 1 minus. So you just refer the properties of the geometric series. So how do you represent the sum of this n terms is like this. So we have 2n1 plus terms. So then the this is the common term. So the common term into the number of terms. So the number of terms is n1 plus 1 divided by 1 minus e to the power. Sorry, so you have another term in front of e to the power j omega n1. E to the power minus j omega. So I apply this geometric series here to replace this finite sum of this. This is a geometric series having a finite sum of this number of terms. So we have a exponential in addition to that, because we realize that once we introduce this index m, so there is a quantity called e to the power j omega capital N1, which is independent of index m. So then we have this e to the power isn't it? Yes. And yes. now you have e to the power j omega n1 and 1 minus e to the power minus j omega 2n1 plus 1 divided by 1 minus e to the power minus j omega. If you have this kind of a form, and if you ask to convert it to a sine function, what we can simply do is we'll do this replacement. Take the half of this exponent, take the half of this exponent and take it out. Okay, take the half of this exponent and that component can be taken into out. So then it's like e to the power minus j omega 2n1 plus 1 divided by 2. Okay, so this is the half. So then we have 1 here. So then it means to make it 1, we need to add a kind of a complex conjugate of this term. E to the power j omega plus 2n1 plus 1 over 2 minus e to the power minus j omega 2n1 plus 1 over 2. So this numerator is done. Denominator also we do the same. So we can take out half of this term, e to the power j omega divided by 2. So then we have e to the power j omega divided by 2 minus e to the power minus j omega divided by 2. Okay, now we can simply convert it to these sine functions. So this is a sine. So you can replace this as a like, so you can replace this as 2 times j into sine this omega. So if you divide this one, it's like n1 plus half. Here you can replace it with 2j sine omega over 2. So then you can cancel these two together. So then this can be simplified to, so we have multiple factors there. So we have j omega n. So we'll put j omega. We have n1 here. And here we have minus n1 minus half. Here we have plus half. So then once you simplify it, minus n1 to my plus n1 minus half, so this becomes simply 0. So then we can simply say that, so this whatever these components are simply converge to 1. Because here plus n1 is there, here minus n1, then we have minus half here. Once you bring this minus half to the numerator, it becomes plus half. So then the ultimately, so this basically converts to e to the power j0. So then we have sine omega n1 plus half divided by sine omega over 2. So this is the final answer. Yes, so could you explain part A of the question 3? So why in E terms in 1? No, that is a 2 and 1 is actually divided by 2. Here, so we have 2 and 1 plus 1 divided by 2, because we simply take half of this exponent out. So then only we can make a kind of a sine term here. So we can have a kind of a 2 complex exponential terms and to make it sine. So that's why we basically take the half of this term out. So then if you divide it separately, so you have n1 plus half. Okay. No, there's sign in the first term in the equation. So so you mean here? So this is actually coming from this substitution. So if you remember, so we had this kind of a summation. Sum m goes from 0 to 2n 1. So we have e to the power minus j omega. And here instead of n, initially we have n, now we make it to m. So the substitution is m equals n plus n1. So once you make replace n with m, so this becomes m minus n1. So then if you expand these exponential terms, so we have a kind of a e to the power j omega plus n1. So we have a term coming out from these. So we have e to the power minus j omega m. In addition, we have e to the power plus j omega n1, which is independent of this index m. So we brought it to the front of this summation. So that term is there. So hope it's clear. Yes. So the whole purpose of discussing this example is like there's a kind of a mathematics involved in the simplification. So if you have a kind of a question like this, which is in the form of sign, so this is the way forward. I mean, like if you try it other ways, there may be a chance of getting the final solution, but this is the very simple approach. If you have a kind of a dual-sided sequence, make it a single-sided sequence by introducing a new variable. So then you can easily evaluate the finite sum. So then yes. Okay. So then we'll move to, can we apply DFT for both? Yeah, yes. So you can apply the DFT for both sided. So if you know the C, because like so what you can do is actually, if you want to apply for both sides, so it's like this. So the first sum is actually from minus n1 to minus 1. So then the second one is like 0 to n1. So you can directly apply DFT for this one, because we know that this is a kind of a summation from 0 to n1. So you have n1 plus 1 terms. Keep in mind n1 plus 1 terms, not n1 terms, because including 0, the number of terms is n1 plus 1. So if you consider this one, so you can do it like you can change the index. So this is minus n1 to plus n minus n1. So you can simply make it like 1 to n1. So then this minus 1 is simply absorbed into n. So here we have e to the power minus j omega n. So here you have minus j omega n. So if you simply change the index to plus, okay, 1 to n1. So what we simply do is actually, so we introduce another variable like n replace with minus n. So that nothing else. So then 1 to cap n1, and that negative sign is simply absorbed into here. So then your exponential would be a kind of a plus e to the power j omega n. So then you can simply apply the geometric series for this first sum and the second term, and do it. And keep in mind in this case, so this start from 1. Okay. So this start from 1 to n1. So you have n1 terms only. But if you apply a geometric series, so the geometric series is normally starting from 1 to 0 to n1. So this is 1 to n1. So if you apply it, so it should be like 1 minus this sum. This sum 0 to n1. So then we have similarly like n1 plus 1 terms like in the other sum. So you have 1 minus is there, because so this is starting from 1, index 1. So the standard geometric series starting from 0 to some x value, n value. So then this you have to remove the rest of the sum. So this is plus actually. No, sorry. So you have -1. So you can basically apply this DFT for this right hand side sequence and left hand side sequence. But if you are developing the answer from the scratch, the easiest way is to make it a kind of a single sided sequence. So according to the question, so one is asking like we have xn like 1100. So if you want to apply find the DFT, so you can just evaluate x omega by just applying xn e to the power j omega n. So then this infinite sum is restricted to a finite sum of 4 samples. So it's here like so we don't know where this sequence is starting from. So depending on that, this may be a kind of a single sided or double sided. For example, if this is the starting point, so this become like a single side. If your reference is somewhere here, so you have both sides. So according to that, you can just have this summation. So for if you have like a few number of samples, so you can simply write it as a sum of exponential terms. If you have 4 samples, you don't need to worry about this geometric series and so on. You can just write this 4 exponential terms by substituting this n value from 0 to whatever, or minus value to plus value, depending on the starting point of this xn. So then you have 4 exponential terms. Sometimes you can combine these exponentials and make it to kind of a sinusoidal or cosine function by replacing this exponential by combining this. So it's depend on the exponent of this terms. So in general, you can if it is like a 2-3 terms, you can simply represent it as a finite number of exponentials. So then you can think of whether we can simplify or boils down these 4 exponentials to a kind of a sinusoidal or cosine, depending on the exponential factors. If it is a kind of unknown number, if your number of samples is n1, whether you don't know what is the value of n1, or if it is infinite, so then you can simply refer the geometric series. Otherwise, if the number of terms are very limited, like n equals 3, 4, so you can just have a kind of a sum of complex exponentials terms. It's fine. And if you really need to make it discrete, so you can simply replace this omega with 2 phi KON. So, but it doesn't have any meaningful value, because if you know the x omega, you can simply replace it with a particular substitution. For this case, you have to find the capital N as well. No? So then it's wise to keep the Fourier transform in this format, or else you can convert it to xk by applying the substitution. Doesn't matter. For this case, I mean like so it's depend on like what I highlighted here is like if xn is like 1100 like this. So then it means, so this is n equals 0. This is 1, this is 2, this is -1. For this kind of a limited, I mean a finite sequence having like very limited terms, so you don't need to convert it to a kind of a single-sided sequence, because you can just apply this fundamental formula and you can simply represent this as a like e to the power plus j omega plus 1. So the rest is simply 0. So it's like 1 plus e to the power j. So this is the Fourier transform. So for this kind of a cases, you don't need to, because the one we referred is actually a generalized sequence where you have this n1 terms. We don't know the value of n1, so then the answer should be definitely in a general format. So that's why we had to refer the geometric series. If you know the number of terms and if it is a kind of a manageable, so you can just indicate it as a kind of a sum of exponential term. It doesn't matter. So the next is actually okay. So this is another example from this filters. Yes. So now you have a kind of idea what would be the phi r, and what about non-recursive difference equation. So here yn, which is our output, is simply represented as a k goes from minus n to plus m bk x n minus k. So for this particular case, your output is simply depends on the values of x. Okay, so if you expand this, so it's like b minus n x n plus capital, sorry, n plus capital. So then k equals 0, we have b0 xn, k equals 1, b1 xn minus 1 plus, then the k equals capital M b m x n minus m. Okay. So by looking at this one, you can simply say that this for this particular system, your output only depends on the input, because we have xn terms are there. So this is the present xn. So this is the present value. So this is the present value of your input. So these are basically past values of your input. Xn. So these are having these plus n's. So these are actually future values of xn. So if you have future values in your terms, so this is not a causal system, non-causal, because we know that if it is a causal system, it should depend on the present input and the past input only. So if it is depends on future input, so this is not a causal system. And this is a recursive, because this, for this particular case, your output is only depends on x. So it's not depend on the previous states of y. So for example, if you have this kind of a scenario, So if you have this kind of a term in your system response, so here you have a kind of so this is your output, so it's depend on input, yes, and in addition to the input it depends on the previous state of the output. So this is actually previous state of the output. So if it is depend on previous states of the output, this automatically becomes a recursive, because you need, so if you want to evaluate the present value, you need the past value. So you can't evaluate the present value without your previous value. So then it automatically becomes the recursive, because to evaluate the previous value, you need this previous values. So it's become a recursive. So if you have the flavors of your output or the versions of your output, if you have this delayed versions of your output or the previous states of the output, so then the difference equation itself become a recursive. If your output is simply depends on the present state or past future state of inputs only, so it becomes a non-recursive. So this is just a theory. Okay, now we will go to the question. So it's defined so as a, so we have FIR non-recursive difference equation like this, and so one frequently used example of such a filter is a moving average filter. We don't know what is actually moving average filter. Doesn't matter, where the input output relationship is given by this. So for the moving average, so this is the relationship. Yn equals 1 over n plus m plus 1 sum k goes from minus n to plus m x n minus k. So if you simply refer this original equation, difference equation, so what is this bk? We know that if you have a kind of a system having a system transfer function hn, and if you fed a input xn, what would be your yn? So yn is actually simply the convolution of hn and xn. So how do you represent the convolution? It's a sum of hk xn minus k. K goes from some index to some index. So this is the convolution. So then if you refer it with this original difference equation, so for this case, bk is actually the impulse response of the system. Okay, impulse response hn of the system. So then if you map it to this, if you map the same concept to here, so you can rewrite it like this. So you can bring this term inside because it's a constant independent of this k. So then it becomes k goes from minus n to m 1 over n plus m plus 1 xn minus k. Okay. So then if you simply match these equations together, this one, and this one, you can simply identify that the hn would be what? According to this, you can claim that your hn is actually 1 over n plus m plus 1 if it is in between this and 0 otherwise. Did you get the point? So this factor is basically representing this Hn. So n plus m plus 1 is a constant. Now fortunately your system response or the impulse response of the system is a kind of a constant. So if you plot it, it's like this. So this is like this. So the value here is 1 over n plus m plus 1. So here we have minus n1 index, here we have m, this is 0. So this is your Hn. So this is your Hn. Okay, so now based on this definition, you can simply claim that the impulse response of the system is like this. It's like this. So then it's clear impulse response of this rectangle is this, otherwise 0. So we derived it. So it's just mapping these fundamental formulas. Nothing to deal with this moving average filter or something. So this is simple maths. So you just combine these two together and see what the Hn would be. So then it's asked to prove the frequency domain translation can be written as, so this H omega can be like this. So how do you get this one? Because we know that this is your Hn. Now this is your Hn. It's a double side sequence because it simply goes from minus n1 to plus n1 m. So then how do you apply or evaluate H omega? So once you apply this fundamental formula of transforming this discrete signal Hn to Fourier domain, so you will ended up with a kind of a double-sided sequence. So if it is a double-sided sequence, you can simply convert it into a single-sided sequence by substituting a new index variable. So then you can follow the same step which we discussed just before, and you can definitely get this answer. So I'm simply skipping that one. So this is already done. So only thing is, like, once you get this section, you should be clear about that this is a double-sided sequence, dual-side sequence. Okay, so dual-side sequence. So if it is a dual side sequence, so the only way is like you can convert it to a single side sequence by replacing the index with a new variable. So then you can simplify it as discussed in the previous case. Yes, hope it's clear, but because nothing here new, so you just combine it with this, the very generic formula and the transfer function or the system form difference equation, and try to find out what would be the Hn. Yes, then we'll move to the next example. Yes. So this is the question 2 part A in the last exam. So this is the part B of this question 2. Okay. So this is again a kind of a question, but by looking at this one, you may feel like, oh, this is not learned before. So we'll try to understand what they are telling here. So it's a non-recursive filter. We know that what is non-recursive filter. So this is non-recursive. By looking at the response, we can see like your yn is depends on this xn. So this is non-recursive, done. And also be used to perform high pass filtering operation. So high pass means like if you plot the response, so omega, so it's something like that. So you have 5 here, you have 0, it should be something like that. Ideal of high pass, it's something like that. So we may have like omega c, whatever the frequencies between omega c and phi is simply filtered out. This is high pass. Okay. So this is high pass filter. So we know that as well. So then the difference equation is yn equals xn minus 1 or 2 and derive the frequency response of the system. Yes, now we asked to derive the frequency response. Okay, so yn equals, I'll simply expand this one. So it's like half xn minus half xn minus 1. So let's again refer the previous equation. If you remember, you can simply say that bk xn minus k. So this is actually bk's are actually the samples of the hn. If you simply refer the previous one, we found that whatever the coefficients in front of this delayed version of input, so they are the tap or the samples of the hn. Okay. So if then like if we expand it for these first two values, so this become p0 xn plus b1 xn minus 1. So it means, so this refers the h0, this refers h1. So your hn is actually now, it's like this, half minus half 0. So this is your hn. So nothing else. So we just refer back to the general formula, which gives the a characteristic of a system through a difference equation. So then the coefficients of this x and delayed versions basically give the coefficients or the taps of the filter or whatever this system. So based on that, we found that this half is representing the first tap or the first coefficient of the filter. So this minus half represent the second tap or second coefficient of the filter. And so other than that, we don't have any term. So then the rest of the response is simply 0. So this is your impulse response. So this is impulse response of your filter, of your system. For this case, it's a filter, but in general, this is the system impulse response. hn is half minus half, rest is 0. Okay. So then we'll, so now we know that, so this is your hn. Now we need to find h omega. So we need to apply this Fourier concept. So we have to apply the Fourier transform. So see how we can apply. So h omega, according to the definition, it's like hn Hn e to the power minus j omega n. Here you have n goes from minus infinity plus infinity, but for this case you have two values. One is actually h0 or the n equals 0, the other one is n equals 1. So then you can simplify it. So we have h0, which is half e to the power minus j omega, n0 means it's just 1. Then minus half then we have, this is h1 e to the power minus j omega. So hope it's clear. Okay, now we have this. So this is h omega, it's equals half 1 minus e to the power minus j omega. Okay, we'll do the same transformation we did for the previous cases. We'll take half of the exponent out, e to the power minus j omega over 2. So then this becomes e to the power j omega over 2 minus e to the power minus j omega. So then we'll convert it to sinusoid. Yeah? So then this becomes actually 2j times sine omega over 2. Okay, this 2 is cancels out. So if you simplify it, it's something like that. So you have j term and e to the power j5. So I'll write it j e to the power minus j omega over 2 and sine omega over 2. So if you further simplify, so if you remember, so if you have j terms there in the expression, we learned that we can replace these j terms with this to make it a phase, j5 by 2. Because e to the power j5 by 2 is actually cos 5 by 2 plus j sine 5 by 2. So sine 5 by 2 is 1, cos 5 by 2 is 0. So this becomes j. So if you have j terms in expression, you can simply absorb this j term as a phase of e to the power j5 by 2. So then we can simply represent this j times e to the power as a phase term. So now this becomes sine omega over 2 e to the power j omega over 2 minus 5 by 2. So I'll just absorb this j term to here, add in this 5 by 2 term. So then, yeah, so this is the response or the Fourier transform of the signal. So then we can simply claim that this part is the phase. So this is your phase response of the filter. So this is the phase response of the filter. So this is the magnitude. So this is amplitude. So if you want to make it a magnitude, so we can simply claim that the mod h omega is actually mod of the sine omega over 2. Because we know that sine component is So they have these positives and negatives. So to make it positive, to make it magnitude. So if you want to get the magnitude, so you have to take the absolute value of this one. Okay, done. So now we can claim that this is the magnitude. So we can simply get the magnitude response from this sine omega over 2 magnitude. So let's plot this one and see what would be the response. So now this h omega is magnitude sine omega over 2. So let's see, like we plot it. So this is your omega. So this is mod h omega, the magnitude response sine. So this is 0, this is 5, this is 5 by 2. So we know that the Fourier transform is simply a periodic in between -5 and +1. So we just plot the half of this one. So positive half of this one, 0 to 5. What about sine when this omega equals 5? Sine 5 over 2. So it is actually 1. So here. So what about omega equals 5 by 2? So it's like sine 5 over 4. It's like some positive value, 3 or root 2, root 3 or whatever, some. One or root 2, if I remember, yes. So omega equals 0. So then sine 0. So it's simply 0. So then if you draw the response, it's something like that. Okay, it's something like that. This is the response. So this may be convex or concave, doesn't matter what I want to show. It's like, so the values of so the when this omega equals 0, it has a 0 gain. When omega equals 5, it has a unity gain. So then what would be the filter characteristic of this one? This is approximately a high pass filter, isn't it? So high pass filter. So it basically passed the frequencies of omega equals 5 means, so the high frequencies, because we know that once you map this real frequency domain to 0 to 5, so all these low frequencies appear here, low frequencies appear here, so the high frequencies appear close to 5. So this is a kind of a high pass filter. So by looking at the magnitude response, we can simply claim that this is a kind of a high pass filter. Yes, actually, so someone asked, yes, someone dropped a message like I need to go refer the part C. Question 1 part C. Just whether we discuss it. Yes, so we already discussed the question one of this part C. So yes, I believe like so the questions I want to discuss here is already done. And so could you explain the part of the part A of question 3? Part A. So if I explain all the stuff, so then it may be basically support to your final exams also. Part A of question C3. Signal exam. Signal. Yes. So there's a one student want to get the answer for the question 3 part A. Could you please drop me a email, so I'll share the answer, or I'll guide you how to get the final solution. So regarding the exam, so it's a open book exam, so you can refer whatever the material you basically have it in your hand, or if you want, you can refer the internet. I don't mind. So what I want is like logical answers for the questions. So it basically contain 5 questions. So this time and the marks are not uniformly or evenly distributed across the yes, sir. After this session, Ishan will take this one. So he too want to discuss some examples. So better you can ask this butterfly note and this signal flow diagrams from him. Um, so what I want to highlight is exam is actually 175-minute one. So it's close to 3 hours and contains 5 questions. So those questions carry, it's not carry equal marks. So there's simply mismatch of this. So those are not carrying 20 marks per each. So depending on the content and the length of the or the depth of the answers, so it carries like different marks, 20, 20, 15, 25 like this. And the time allocated for these questions also differ from question 1 to question 2 and so on. And so this is delivered as a question by question mode. So the first question is appear. And for example, this we'll assign a kind of a 30-minute for the question. So the first question is appear from 9 to 9:30. So then you have a 10-minute buffer time to upload your answer to the Moodle. So keep in mind, upload it as a PDF format. And also check whether what you have uploaded. Sometimes you are uploading empty files. Sometimes you are uploading some image files. So the system is by default restricted into PDF. So please note that only PDF copies are accepted. So anyway, you have to make it to a PDF. Either you can install a kind of a software to the mobile phone like CAMSCOM scanner and make it to a PDF. And from 9:30 to 9:40, so it's a buffer time for the first question. So you can upload the answer as a PDF to the Moodle. So we'll give an additional 5 minutes as an extended buffer time if somebody realize a kind of a poor internet connection, because otherwise your link is simply disappear within 10 minutes time. So it's all together appear there for 15 minutes time. First 10 minutes is the standard buffer time. So the last 5 minutes is the actually extended buffer time. If you really feel some bad internet connection, so that 5 minutes can be utilized to upload it to the Moodle. But that 5 minutes is simply taken it up from your question 2, because from 9:40 onward, the second question is appear in the Moodle. Okay, so you have 10 minutes standard buffer time from 9:30 to 9:40. Then the second question is appear from 9:40 onwards. But at the same time, you have another 5 minutes time to upload the answer for the first question if you have a kind of a if you experience a kind of a trouble once you are uploading. So if you can't upload it within that buffer time, you whatever the 15 minutes buffer time, so the uploading link will be simply disappear. So then after the exam, so we basically have another link appear in the Moodle. So it's a kind of a late submission. So whatever the missing upload should be submitted to that link. So don't send it to exam or somebody else. So just upload all these files to this whatever this link appear after the exam as a late submission. Because once you send it to the exams and so on, I am getting part of the emails, and sometimes I felt like I didn't mark some exam papers which are basically comes through examination as late submission. So keep in mind, whatever the late submission should be uploaded into this late submission link. It may be question 1, question 2, question 3, 4, 5, 6. I don't mind. So you should upload it to there. So then I can guarantee that all these answer script are there in the Moodle, and I can go through these and mark. Okay. So this is the format of the paper for the late submission we have. It depends, like because sometimes it's unfair. If it is like I didn't decide that what could be the penalty for this late submission, but we'll see. Like, so if you because it's something unfair for other students who try to submit it within the buffer time. So we'll see, like I can check with the quality assurance team and see. So do we have, yes, so each and every question, so you have several parts. So this part can be selected based on the last digit of your index number or student number. So mostly there will be a kind of a penalty for the late submission. Try to upload it within the given time, because like for an example, for the question, you have 45 minutes to do whatever, right? Because I am planning the question. So if it is 30 minutes, you can basically finish it within 25. So then you have extra 5 minutes also there. So you have basically 20 minutes to upload it. So try your best to upload it to the whatever the link appear as a submission link. So there's sometimes the late submission may carry some penalty. And yes, like as question here, so you have to have prepare for multiple questions. So these question may not be exactly same as the others getting. So it's depend on the in last digit of your registration or the student number. So based on that, you can select the parts of the questions and write it and upload the PDF to the Moodle. So this is done. Yes, Ishan, you are there in the session?
Yes, sir. Yes, sir. Yes, sir.
Yeah. So you are there, no?
Yes, sir.
So I'll transfer host to you.
Sam.
So you can
Okay.
continue from this point.
Okay, sir. Thank you.
Ishan, I can't hear you. I don't know whether it's my fault. So anyway, I'll transfer the host to you, but it's not audible, I guess. So your mic is working, but so we, okay, so you can discuss some examples with them. So I'll leave from the session.
Can you hear me?